Good afternoon, everyone. I'm Wang from Shanghai Jiao University, China. I'm honored to have the opportunity to share our work with you. And the title of my report today is A Novel Approach to Air Quality Monitoring Towards Miniature Self-Organized and Low-Power Device. Sorry. My report contains 4 parts. The first part is background. Monitoring air quality is very important because it directly affects public health, ecosystems, and the economic structures. In the past, air quality monitoring was centralized and used bulky power-intensive setups with delayed data analysis. However, as technology advanced, the way we monitor the environmental attributes changed. Quantitative analysis provides more accurate and reliable data than qualitative analysis, helping the scientists and the government departments to better understand and assess the air quality. Besides, the application scenarios of the gas sensing can be significantly expanded. Artificial olfactory system, also known as the electronic nose, that is the use of the instruments to simulate the olfactory function of the mammals to achieve the perception of odors, which mainly consists of 3 main parts, including gas sensing arrays, signal processing, and pattern recognition. Compared with the traditional gas phase analyzers, the electronic nodes are more portable and smarter, which advantages and the potential for large-scale applications. So the second part is the low-power air quality detection node. Our device consists of 2 layered PCBs, resulting in a sleek design with small size. We chose the SHG20 and the SGP40 sensors for temperature, humidity detection, and the VOC monitoring. Meanwhile, the SHG20 readings are utilized for the baseline composition of the SGP40. The device uses the low-power STM32 L432 microcontroller as the main control unit. A ZigBee wellness module is integrated for the establishing a robust ad hoc network powered by a 60 mAh lithium battery. The device features a charging management circuit optimized for the solar cell charging, which also supporting the USB Type-C charging. So we utilize the background registers of the microcontroller to realize the saving and the restoration of the crucial system data between the sleep and the wake up state, which improves the execution efficiency of the system. We designed for 3 main operation modes, including high performance mode, DAQ mode, and monitoring mode, to meet the need of the battery life in different scenarios. Considering that the SGP40 is a typical MOS gas sensor, it requires a warm-up time from startup to operation. Therefore, an operating rhythm of long and short cycles in monitoring mode is designed, where the fast starting units, such as MCU and SH20, work on short cycles, while the SGP40 works on long cycles to minimize the repetitions of the heat on and off. This figure shows the architecture of an air quality monitoring network. The main device collects data such as VOC, temperature, and humidity updates. They are powered by solar cells when possible. The key device acts as our network relays in high performance mode and are powered externally. ZigBee modules are used as coordinator, router, and end device respectively to create an ad hoc network with the efficient power management, reducing the maintenance needs. As you can see, this figure shows how long the device lasts on a 60 mAh lithium battery in DAQ mode and monitoring mode. In DAQ mode, the device lasts for 8 hours before needing a recharge. In monitoring mode, the device lasts for 14 hours. When adding solar cells outside or extending the sleep phase, we can lengthen the operational time. In DAQ mode, The standby current is about 2.7 million ampere due to the heating of the SGP40. The working current can pick up at 2 milliampere due to the LC operation and the ZigBee data transmission. Monitoring mode operates in a similar pattern, but you can see the long sleep phase drops the standby current to about 45 microampere, allowing up to more than 1,300 hours of standby time. The figure A and B shows the VOC readings change as the ethanol concentration increases from 10 to 100 ppm. Figure C and D demonstrate that the SGP40's periodic operation has no effect on the ethanol response, which stays consistent without any drift or decline of the performance. Finally, you can see figure E is a close-up of the figure C, which illustrates SGP40's preheating process to 20 ppm ethanol. Initial readings increase before stabilizing, indicating a rise in temperature of the sensing material. The third part is the temperature modification enhanced eNodes. It's worth noting that cycling the SGP40 on and off has two effects. First, it changes the output form and operation state of the sensor. Secondly, it can greatly decrease the sensor's heating power. And there are many studies have shown that the identification performance of the gas sensors can be further enhanced by using the temperature modification method. Therefore, we conduct additional research to examine how temperature modification can reduce power usage and improve the performance. We designed the hardware of the eNodes using the two commercial MEMS gas sensor. The system is equipped with a STM32 F103 MCU, which with a 32-bit ARM Cortex-M3 core. The data acquisition uses the on-chip ADC, while a LoRa module ensures the wireless communication. The figure A and B displays the eNodes PCB layout and 3D rendering picture. Jiaqing's compact design. Figure C and D isolate the temperature modification circuit and the front-end conditioning circuit of the eNodes. Sorry. Okay. This diagram compares the sensor output between the temperature modification mode and the common constant temperature mode. In the modification mode, as you can see, the sensor's output fluctuates with the temperature changes and shows different response characteristics as presented in the figure C. The signal is decomposed into a number of outputs, similar to those in constant temperature mode. Considering the limitations of the edge computing, the up and lower developers are directly adapted to obtain two sensing signals as shown in figure D. It's like the signal output of the constant temperature mode. Sensor signals may have multiple labels based on the gas type or the concentration. The chosen feature data is the steady state of the response of the sensor. And the feature data undergo a PCA dimensionality reduction and the cluster analysis. The PCA process data colored by the concentration and the category shows some clustering but with some overlaps. And you can see the category-based clustering is more distinct than the concentration-based clustering, which indicates the different difficulty between the two tasks. As you can see in this figure, classification models trained using the temperature modification-based data obviously have faster convergence than the models trained using the constant temperature-based data. Temperature modification can bring about periodic temperature changes of the sensitive material, which in turn generates richer sensory information to improve the performance of the trained model. From the comparing of the confusion matrix, it's clear that the classification model based on temperature modification mode significantly outperforms the model based on the constant temperature mode. However, in the regression task, the models trained in both modes performs both poorly, which indicates that the regression task is more challenging, while the artificial neural network of the edge computing are not complex enough. Besides, temperature modification sacrifices some of the sensor's response performance at both high and low concentrations, so resulting in a lower accuracy of the regression model. The first part is conclusions. In summary, we report a low power air quality dictation node for building a large-scale air monitoring network. The dictation node can realize the establishment of the ad hoc network, VOC dictation, and long standby time. We further investigate the temperature modification technique for power reduction and performance enhancement through the efficient algorithm we designed. We realize edge computing for data processing and pattern recognition in an ARM Cortex-M3 based MCU. We designed signal reconstruction methods for processing temperature modified signals. Our work demonstrates how temperature modification improves the sensor performance and reduces the power consumption, which has a significant importance to improving low power air quality detection node. Finally, I would like to thank all the staff of our research team for their diligent and creative work. Our research team runs a journal named Nanomicronatters, whose impact factor is over 26. Our journal focuses on the research area of nanosensors, nanobiomedicine, nanofunctional materials, and so on. So we welcome submissions to our journal. That's all. Thank you.